see we have quite a full attendee list, so thank you for joining us. Welcome to our special Elektor webinar, Reverse Engineering Bluetooth Low Energy Devices. I'm Brian Tristan Williams, your host for today and an editor for Elektor magazine. So whether you're a tech enthusiast or a seasoned developer or someone just curious about the cutting edge world of BLE technology, you're in for a treat. We've got an action-packed session ahead of us designed to unravel the mysteries of BLE devices. And I'm joining you from Aachen in Germany. And author Koen Vervloesem, an expert, is joining us all the way from Aachen in Germany. We're in the same room, which is quite novel. That's hence these backgrounds aren't fake. This is real. And he's a distinguished tech expert with over 20 years of experience in Linux, IoT, and everything in between. And he is the author of this relevant book, Develop Your Own Bluetooth Low Energy Applications, from Elektor Publishing. I've been through this book. I've done a lot of the experiments. I was fortunate enough to be involved in the editing process last year. So it's a lot of good stuff in here. And Koen was kind enough to join us to take us through a lot of his experiments and to show us some of his tricks. So from exploring device characteristics to sniffing BLE traffic and even decompiling mobile apps, we'll give you the tools to understand and interact with BLE devices on a whole new level. Get ready for interactive demos and exercises that will put your newfound knowledge to the test. And hey, stick around to the end because we've got a special giveaway. 5 of you lucky attendees will win a copy of Koen's invaluable book on BLE communication and reverse engineering. So sit back, grab a coffee, and let's dive into the fascinating world of Bluetooth low energy reverse engineering. Over to you, Koen.
Thank you, Brian. So reverse engineering Bluetooth low energy devices is a topic, but where did it all start? I had some Bluetooth clocks. And a Bluetooth clock is just a clock like this one I have here. I have a clock and it shows the temperature, the clock, the humidity, but also another clock, this one, smaller one. It also shows the temperature, humidity, and a clock, and also this one. So I had various clocks around my house. And if I wanted to synchronize their time, I had to use an app. But for this one, I had to use an app from the Thermo Pro device. For this one, it was another app. And the third one, it was another app. I had, for every clock I wanted to synchronize the time, I had to use another app. Now, there are some standardized modes to synchronize the time. The Bluetooth protocol has standardized the current time service. But none of these clocks were using the standard. So each of the vendors had implemented their own custom formats to synchronize the time with these devices. So I just had to use these different apps, and I thought this should be more easy to do. I should have one way to synchronize all my clocks in the house instead of opening this one app, then the other app, and then a third app just to synchronize my clocks. So this is when the idea started to try to figure out how do these apps synchronize their time with the clock. So then I just have to take a step back. How does Bluetooth communication work? Bluetooth low energy devices have 2 ways to communicate. There's one way, broadcasting, and another way, connecting. Broadcasting is actually, many of these clocks I had also a temperature sensor, and they just broadcast their temperature to anyone in the neighborhood. So any Bluetooth device in the neighborhood, your phone, your computer, other Bluetooth devices, they can receive these advertisements. These advertisements are just some bytes of data that have the temperature and the humidity and the battery status in them. So that's one way to communicate with the BLE device, and that's the easiest way. Everyone can pick up these data and just observe them. But the other way is by making a connection. So the broadcasting is actually a one-to-many communication, but connecting is when one device connects to another one. And that's, in this example, what the app is doing. If you want to synchronize the time, the app is connecting to this device, connects to it, and writes the current time to the device, and then disconnects. So that's a one-to-one connection. And that's a bit more difficult to try to figure out, because you have to sniff the traffic, the Bluetooth traffic on the air between the app and the Bluetooth device. So the rest of this presentation will be about this second way of communication, connecting. So when I saw, okay, I want to try to figure out how to synchronize the time with these clocks, I came up with an attack plan. And the attack plan is here on next slide. What I want to do, or what I should do is, okay, I have this communication going on between my Android phone and the clock. So I just intercept all the BLE packets between the Android phone and the clock. Then I'll let this app connect to the clock, let it synchronize the time. And then in this communication, I have to find the command that the app is sending to the clock to synchronize the time. And when I find this command, I have to decode it. I have to find out which byte is representing the current year, the month, the day, the time. And if I figure this out, I can re-implement the same synchronization command, and then, for example, in a Python script, and then I can run this Python script, connect to the clock, and run this or connect and write the synchronization command to synchronize the time in my own script. And if I have this script, I can run this whenever I want, for example, once a day on a Raspberry Pi, and then I have my solution. I don't need the app anymore. I can just synchronize the time with this clock, but also with this clock if I figure out its synchronization command, and with the other clocks. And I just have to repeat this process, this attack plan for each clock. That was what I came up with the attack plan. So I did this, and in this presentation, I show how I did this for this specific clock, the TP358 from Thermopro. It's one of several clocks of this type, some bigger, some smaller, from the same vendor, and they all have the same, they all support the same command. So once I figured out the time synchronization command for this clock, I was also able to synchronize the time for other clocks of the same vendor. So if we're looking at how I implemented this plan for this clock, let's see this in the next slide. The first step is intercepting the BLE traffic. Now, there are various ways to intercept this traffic. One option is you connect with this device and you intercept the traffic in the air. There are various devices that you can use for it. On the slide, you see Nordic Semiconductor NRF52840 dongle. It's a popular Bluetooth low energy development board. It's really a small dongle. You can put this in your laptop. You put some sniffer firmware on it. The sniffer firmware just listens to all radio packets that are Bluetooth low energy, and it intercepts them, and it sends them on a USB serial connection to the computer. And then on the computer, you have a plugin for a capture program that captures these packets, and then you can see live through all the BLE traffic. So that's one option, intercept the BLE traffic in the air. Now, the other option is just intercept the traffic on the phone. So you can, in Android, for example, you can enable a lock, the HCI Snoop lock. HCI stands for host controller interface. It's a part of the Bluetooth low energy protocol stack. So if you enable this HCI Snoop lock in your Android developer options, and if you enable USB debugging, then you just connect your phone using USB to your computer. Then you use the app on your phone to connect to the Bluetooth clock, and then you can follow the BLE traffic live, because the Android phone is sending the BLE traffic over USB to your packet capture software on the computer. So you can use this as a packet sniffer, but then you're not intercepting the traffic in the air, but on the phone itself. Another way is to let this phone just intercept this traffic on the phone, but write it to a log file, and then you can later open this log file in your packet capture software. So you can do it live, or you can do it afterwards. So this is the part really about intercepting the traffic, but you need another part. You need to be able to look at these packets, and that's with Wireshark that you're going to do this with Wireshark. It's a popular network protocol analyzer software. Many network system administrators and network administrators will be comfortable with it, will be using it for looking at the network traffic on their Ethernet or Wi-Fi network. But with BLE plugin that comes with the NRF sniffer firmware, for example, you can take a look at the BLE traffic. So then you put this dongle in your computer, for example, with the sniffer firmware. It sends all the packets, the BLE packets it receives through the USB interface to the computer. Wireshark receives these packets and shows them in this screen you're seeing here. So each of these lines is one BLE packet that is received, and then you can, for example, above in the green bar, you can enter display filters, so you can filter the traffic to limit the type of packets you want to see. And at the bottom, if you select one of these packets, at the bottom you can see the full content, and you can see the decoding for the different parts of the BLE protocol stack and the actual data that goes into it. So this part, so the sniffer dongle or the Snoop lock on the Android phone on the one end, and then this Wireshark capture software. These two parts together, you will use this to intercept and investigate the BLE traffic. And by doing this and looking through these packets, I was able to figure out which commands are sent from the phone to the clock to synchronize the time. So that's the next step, figuring out this time synchronization command. So you have lots of BLE packets flowing through the air, and you can see them flowing into Wireshark. It's really a lot of traffic, not only from this device, but also from any other device in the neighborhood. If you remember one of the first slides where I talked about the two types of BLE communication, there's on the one hand broadcasting, the other hand connecting. Many BLE devices are broadcasting information around you every time. Phones, BLE, clocks, temperature sensors, all sorts of sensor devices are continuously broadcasting their data. So all this data is flowing through Wireshark. So you have to find the specific time synchronization commands. It's a bit like finding a needle in a haystack. So the attack plan then is not, don't try to intercept all traffic, but limit it as much as possible. So how to figure out this time synchronization command? You have to limit the traffic as much as possible. So we start intercepting the BLE traffic in Wireshark, then let the app connect to the BLE clock, wait until the time on the BLE clock is synchronized, then write down the current date and time, because you have to find this in the data, and then immediately close the app and stop intercepting the BLE traffic. This way, you limit the number of packets by starting just before you connect and by stopping immediately after you close the app. So you have a haystack as small as possible then, because you know the time synchronization command is in this intercepted traffic, but you have to go through all of them in principle. So, but you don't really have to go through all of them. You can use some information, because the most important information you know is it's a write request, because you connect with the Android phone to this clock, and you need to write, you need to synchronize the time. So you need to send a command with a time to the clock. So what is this sending a command? That is a write request. It's one type of BLE packet. So fortunately, you can, in Wireshark, you can apply a display filter, like I showed in the previous slides. So you enter a display filter at the top in the green bar, and then you can filter to only see the packets that are write requests, and then the lots of data flowing around is really limited to just these packets that are a write request. Then you can go through these write requests and you start investigating each of them. And in this case, the app connected to the device. And in this case, the first write request was already the second write request, I remember, was already the time synchronization command. So it was easily found. So, but how do you find them? You just have to look for values in these packets that could represent the date and time you wrote down. It's easier said than done. Sometimes it's easy to really see, okay, this is the current date, this is the current time. Sometimes it's a bit more difficult. So it can be a fun puzzle. It's like finding a needle in a haystack. So in this case, it was quite easy because you could see the year, the month, the day, and so on in the data. But there are other cases where the time, for example, is represented by a Unix timestamp. The Unix timestamp is just a 32-bit value that represents the number of seconds since January 1st, 1970. If you just look at a timestamp like this, it just looks like a random number. You really don't see the month or the year in these data. But if you convert the current time and date, for example, to such a Unix timestamp, you should see this number or a part of this number in the Bluetooth data. So this looks like this. If you investigate these packets, these write requests in Wireshark, you can look at the details and you can see a value like this one. So these are hexadecimal numbers or hexadecimal digits actually. So you see a value like A5, 17, 03, 05, and so on. So you can already see the date and time here. It was on Sunday, March 5, 2023 at 11 and 1 minute, at one minute after 11. So the 17 here, these are hexadecimal digits. So 17 is equal to 16 plus 7, so it's 23. It was the year 23. The 3 was represents March, the third month, and the 5 represents the 5th of March, and then so on. So if you look at all these bytes in this write request, you have this this decoding. So I was able to decode it until, yeah, I saw a couple of them I didn't know really for sure. For example, the A5 and the 5A, the A5 in the beginning and the 5A at the end, I didn't know what it represented. I thought maybe it is a header and a footer. You can see there's a lot in some data formats that they start with a specific byte or stop at a specific byte, just as a check to see if the right format is used. So I expected this to be just a fixed header and a fixed footer. Then, yeah, the year, the month, the day, the hour, and the minutes was actually easy to see. But then there were 2 sevens, and I wasn't sure it was a 7th weekday then. So yeah, is it maybe Sunday? Is a 7 representing Sunday, or is the 7 representing the seconds? But my clock didn't show the seconds, only the hour and the minutes. So I wasn't sure what to make of these 2 sevens. And then there was a 01 at the end, and I really didn't know what is this representing, some Boolean flag. So yeah, I had a decoding, but it wasn't really, I wasn't able to decode all of this. So yeah, I had a partial solution, but I thought, okay, what to do now?
We are going to transition now to a survey, and we'd like to know from you, what BLE device type you would like to reverse engineer. So what are the options there? You've got button, clock, curtain, environmental sensor, lock, scale, a smartwatch or fitness tracker, a thermostat, or the ubiquitous other. I see a lot of you are jumping in, and we'd like to see the results. So take a couple of minutes, Koen, while you're here. How did you get your start in Linux and open source?
How did I get started with Linux and open source? It was university, I remember. I was studying for an engineering degree, and then one of the projects was about some cryptography, and then I don't exactly know why, but the one that was the person that was giving us that project, he just said, "I'm using Linux. You have to use Linux to write this software, and yeah, you just have to install it and yeah, get on with it, install it, and then you can start the project." So I had to install Linux. I had a Mac at that time, and it wasn't really easy to install Linux on a Mac at that time. It was more than 20 years ago. So I installed Linux on my Mac, and yeah, that's how the ball got rolling. And since then, I've always been using Linux on all my devices, and that's how I started. Yeah, using Linux and many open source projects. I really like the approach of Linux and open source software. It's really an approachable community, an approachable way to work. If you want to use something, there's a lot of open source software you just can use, you just can install. You don't need the license keys, you don't need to pay a fee. You just download it, you install it, and that was really a nice way for me to experiment with new software. That's what I like, trying out new software, and that's the open source way.
Yeah, and it was a challenge to you at the beginning, but you've gone as far as to be teaching Linux now.
Yeah, I'm teaching Linux classes too now this year at University College, and it's a nice way to spread my knowledge.
Okay, thanks for that. Let's have a look at these survey results.
I see a lot of environmental sensors, smartwatches, fitness trackers, thermostats. Yeah, environmental sensors are really a popular type of BLE device, because these clocks I'm showing, actually these are also environmental sensors. That they also show the temperature and humidity. I have a lot of temperature and humidity sensors in each of the rooms at my home, and yeah, it's really a popular Bluetooth device. So if you have one of these devices at home and you want to read these temperature and humidity measurements in your own software, that's an interesting puzzle to try to reverse engineer this device.
Okay, that's great. And then for those of you that put other, I'd like to know what that is as well. So drop it in the chat. You can see what else you're building. But back to you, Koen, with the rest of your fascinating presentation.
Okay, so before this questionnaire, I stopped it. I ended with, we have a partial solution. I figured out most of these bytes in the write request to synchronize the time. So actually, I already could use this information to synchronize it. Most of I could synchronize the time with this data, but I really wanted to know these missing pieces. So what did I do? I looked at the mobile app. I thought maybe I can decompile the mobile app. I can look at the source code, the original source code of the app, and I can look at what exactly the app is doing, what exactly the app is sending. So to do this, I had to get the app's APK file. So it's an Android app. Android apps are deployed using APK files. So I have to get this APK file from the phone. You can do it with the Android debug bridge. So you connect your phone using USB to your computer, and with the ADB shell, you can get the app from your phone. Then you have the file. or you can download it from third-party APK downloader sites. There's the APK Pure, for example, and you can just download the APK files. You can't just get them from Google Play Store, for example. They are sort of hidden from there. But if you have this APK file, you can open this in a decompiler app, and one that I've been using for many years is JADX. It's able to decompile the Dalvik bytecode from an Android app into Java classes. So you just open the APK file in JADX, and then it shows you the Java code that actually is the origin of this app. But why didn't I do this first? Because this is even a bigger haystack. You get a lot of code, and inside this code is just one small piece of code that sends this write request, this synchronization command. So this is again finding a needle in a haystack. It's again a fun puzzle, but I didn't want to start with this because it's really not always easy to find the right code in this big pile of code. So to start searching for this code, there's some other information we first have to know. I showed the data in the Wireshark capture. So I looked at the data to send this command, the A5 170305 and so on. That's the data, but we don't just send this data to the device, we then send this data to a specific part of the device. And each Bluetooth device has some specific data containers of the Bluetooth characteristics. The Bluetooth characteristic is the simplest part, the simplest data container, the smallest data container that can be serviced by a Bluetooth device. So each Bluetooth device has various services, and each service can have various characteristics. So a characteristic there is a characteristic, for example, to write the time. There is another characteristic to, for example, read the device name, and so on. So if you look at the Wireshark capture of the Bluetooth packets, and you find this write request to write this data to synchronize a command, we looked at the value first, but now to find the spot in the app that writes this data, we look at the UID of the characteristic, and that's here in the blue part in the screenshot. This data is written to the characteristic with this UID. It's a universally unique identifier. So it's a 128-bit number that is often written in this format, first 8 digits, then 444, and then another 12 with a hyphen between them in these places. So this UID is actually the place where this data is written. So we can use this as a first breadcrumb to find in the source code where is this UID referenced. So then you can in JADX use a text source. So I started to type the UID. I started just typing 0001, the beginning of this UID. I had a few hits, and I immediately saw there at the end, one of the hits at the end is this a constant where this characteristic UID is referenced. So actually this place in the code is defining a public static final UID with a specific name F4 and so on is a UID from string. So this actually defines a constant that is referring to this characteristic UID. So the next step then is, okay, we have found a spot where this constant is defined. Now we have to find a spot where this constant is referenced. So just again, a search, a text source or a usage search. And then here are 2 hits. The first one is the definition we found. And then the second one is a place where this constant is used. So this should be some interesting code because we have to use this constant to write the data. So if you click on that one, then we find the spot where the magic happens. So this is actually a public void public void M048 and so on. This is a method in this Java class, and you can see here that that it creates an array, and it creates a new byte. It creates a time object, and you can see that it extracts from the time the year, the month, the month, day, the hour, the minutes, the seconds, the week, day, and you can find all this information that we found by reverse engineering, by decoding the data on the air. You can find it back here, including the missing pieces I talked about. So if we put it on the next slide in the list, then you can see the A5 in the code, it's written as -91 in decimal. It's this fixed header. And then at the end of 5A, it's written as 90. You can really see in the code, it's just a fixed value that's put there. This, my initial idea that was just a fixed header and footer. It seemed to be the case. And then, yeah, you can see the different spots where the year, the month, the day, and so on are coded in the message. And then here we can see that the first 7 was talking about the second, and the second occurrence of 7 was talking about the 7th weekday, Sunday. And then this mysterious 01 that I thought, what is this? It's some sort of Boolean flag. It was indeed the case. It was a flag that said from it's 1 if you use the 24-hour format, and it's 0 in the other case when you're using the AM PM format on the clock display. This was something I really didn't know before looking at the code, but there are actually 2 ways to show the time on this display. The one way is using just the 24-hour format, and the other way is using the AM and PM format. So by looking at this code, now we have decoded all the unknown bytes. We can put together a time synchronization command to put an arbitrary time into the clock. So now we're here in our attack plan. We have intercepted the BLE traffic. We have figured out the time synchronization command until the last byte. And then what we're doing now is re-implementing this synchronization command in our own code. So my next step was, okay, I know how to synchronize this clock. I wanted to do this in my own Python code so that I could run this Python code on my own Raspberry Pi, for example. So actually the most difficult part is done now. What comes here is just wrapping it all up. So yeah, I wrote this Python script that just first converted an arbitrary time to the command I had to send to the Bluetooth clock. So it's actually not that difficult. I just create a byte array with starting with the header and ending with the footer. I get the timestamp from the current time. I extract the year, the month, the day, hour, minute, and so on, the weekday. And in this case, I just went for the easy way and just used always a 24-hour format. So I wrote this function to get a timestamp as input in Unix timestamp, and then returned this byte array with the command to send to the Bluetooth clock, returned this as its result. And then in the beginning of the code, you see that I defined a constant command char for the characteristic UID I had to use. So this is just the coding the time into a command. And in the next step, you connect to the device. I'm using the Bleak library. Bleak is a cross-platform library for Bluetooth Low Energy in Python. It works on Linux, it works on macOS, it works on Windows. So I'm using here the Bleak client, a Bleak client object to connect to the device. I convert the current time to the bytes, and I write this bytes command to the characteristic defined in this constant in the beginning of the code. And that's it. I just, I have a command line argument for the Bluetooth address of the device, and I just connect to this address. I convert the time to the command, and then I write the command to this characteristic. So that's it. These two slides are just a full code to synchronize the time with this clock. But of course, this is just a simple first quick script. So I had to wrap this up and create a full time synchronization script around this. So that was the next step, because I had this clock, we had another clock, and some other clocks, all having their own time synchronization commands, like I said in the beginning. So what did I do then? I created a Python module with support for all of these clocks I had, and yeah, I wrapped it up and I created a bit something more robust, a robust way to synchronize these clocks with a command line interface to discover clocks in neighborhoods from their advertisements, to connect to a clock and set a specific time to synchronize the time, to get the time. Some of these clocks also can return their current time. You can connect to a clock and ask to the clock, what's your current time? But you can also write the time, and some clocks support the AM/PM format, others don't. So I added support for all these clocks in this one Bluetooth clocks package with an interface, a device-independent interface, device-independent API to set and get the time on all of these. And I published this package on PyPI, so anyone can now just do pip install Bluetooth dash clocks, and then you can use this Bluetooth clocks command to synchronize the clocks you have, or to discover which clocks that you have are supported. This is the supported devices table. So I have this Xiaomi device, I have the Thermo Pro devices, this one and some others. I have some, these are some other devices with some alternative firmware on it, and these are also supported by the Bluetooth clocks package. There's also the current time service is actually a standardized way to synchronize the time. I already referenced it shortly in the beginning. So the current time service is mostly implemented by smartwatches and fitness trackers. So for example, the Pine Time I'm wearing here is, if you're using the Pine Time with the Infinity Time firmware, it's open source firmware, it implements the current time service, so you can connect to this smartwatch from your computer. You can synchronize its time. So yeah, if you're interested, if you have another clock at home and you're interested in doing this exercise, it's a fun puzzle, and you can help me expand this table, hopefully. So I'm open for contributions, for pull requests, if you want to add some code. The package is fully documented, the API is fully documented on Read the Docs. So you can, if you have a look there, and if you look at the code of some of the devices I implemented, it should be quite easy once you have figured out the time synchronization command to write the necessary code to support your device in this package. There's something else I did then. So I had to have created this Bluetooth clocks package to synchronize various types of clocks. But there's another project I'm contributing to, that's Things Gateway. Things Gateway is Python software that is able to decode BLE advertisements from more than 80 devices. So many environmental sensors, tire pressure sensors. Most of them are sensor devices. They're broadcasting their data around, and the Things Gateway project supports the broadcasting format of more than 80 devices. Picks up these advertisements, decodes them, and writes the decoded data to an MQTT broker. And then you can integrate it in your own home automation system, for example, to use this sensor measurement. But Things Gateway was only listening to broadcasting packets. So what did I do? I added the Bluetooth clocks package. I integrated it into Things Gateway, so you could synchronize the time of your Bluetooth clocks that were discovered around you. So thanks to the Bluetooth clocks package integration into Things Gateway, the Things Gateway not only is able to decode various sensor measurements, but will also synchronize the time of the clocks you configure in your Things Gateway configuration file. You just configure these Bluetooth addresses. I want to synchronize their time, and once a day it synchronizes time automatically. So you can just run Things Gateway, for example, on a Raspberry Pi that is running 24/7, and then you're sure all your Bluetooth clocks are always synchronized and always having the correct time. Okay, so this was how I attacked this. This was the attack plan, how I implemented this for the TP358 Bluetooth clock, but this is just one example. Another example I want to show, just to show quickly what is possible by reverse engineering these types of Bluetooth low energy connections. There was this Bluetooth LED badge. I have one with me here. It's some badge. You can write some text on it, and you can write some pictures on it. I found it on AliExpress, but it came with an app. It was an app. You had to install this app, and in this app you could write your texts to send to the badge. You could choose some small icons here in the app, but it was just a fixed list of icons, and I thought, why can't I just create my own icons or a full image to send to this badge? So I started the same way as I did with the clock. Started to sniff the traffic between the app and this device, and I started to look at it. I started to send a picture or a text to it, and had a look at the data. So then I figured out, okay, this command is used for this type of bytes, this type of pixels. So I created my own images in pixel editors such as Pixelorama. I wrote a Python script to connect to the device, to the Bluetooth LED badge, and then write the correct command to write my own images, and then I could put my own images on the badge instead of just the fixed set of icons. So this is just another example of what you can do by reverse engineering Bluetooth devices. In this instance, it was also necessary to look at the code of the app. Okay, so I've shown the clock, how I reverse engineered it. I have shown another example. So to conclude, how reverse engineering BLE devices, how do you do it? It's really not magic. It's not that difficult. The intercepting part of BLE communication is often easy and cheap. You just need such a cheap dongle. It's 10 euros, around 10 euros. There are better dongles like this one. There's an external antenna. It has much better range, but inside it's just the same Nordic Semiconductor board, just with an external antenna. So intercepting the traffic, the BLE communication is quite cheap, and it's easy to do. Figuring out the meaning of these BLE commands can be difficult sometimes, but it's a fun puzzle to do. And then re-implementing these commands in your own software is also quite easy to do. You can use a cross-platform Bleak library like I have been using for the last years. If you're a Python developer, and other programming languages surely have their own easy-to-use BLE libraries. So it's not that difficult to do. I've put some links at the end of the presentation if you want to know more about what I talked about. There's some documentation on Nordic Semiconductor's site about the sniffer, because you have to put some firmware on this dongle, and you have to install the plugin, the capture plugin for Wireshark, but it's documented quite well. And if you're using the HCI Snoop lock in Android, you have to install the ADB. The link is there too. Wireshark is just an open source package you can install for free from its website. JADX, the decompiler, is also free software you can just download. Bleak is excellent documentation on ReadDocs. I've also put some documentation about Bluetooth clocks, my Bluetooth clock synchronization package. I've also put it online. And for Things Gateway, they have also extensive documentation about what devices they support. And I have also my own website where I regularly blog about Bluetooth and other topics I have been writing about. Okay, and then I have this book. I've written this book about Bluetooth low energy applications, and the example with the Bluetooth badge here is actually taken from one of the chapters of this book, where I explain in detail how to reverse engineer this device. Okay, this is the end of my presentation. I hope you've all enjoyed it, and probably you will have some questions.
Yes, indeed. And as David said, excellent presentation. Don't forget, audience, we have a special treat for attendees today. We're giving away 5 copies of Koen's indispensable book, Develop Your Own Bluetooth Low Energy Applications. Now, these will be delivered to you directly because we're giving away the ebooks. To enter the giveaway, just head over to the link that you'll see, click on the button, and the code word for today to remember is BLE. It's a fantastic resource filled with insights and hands-on techniques, so don't miss your chance to snag a copy. The question we always get is, will the slides be available? Well, the video will be available on our YouTube channel. You can head over to elektor.tv, and that will take you through to YouTube, and the video will be up very soon. The slides will be visible there as well, and if you really want to deep dive, get the book, as you see on the screen. Here's part of the book. That's part of what you saw in the presentation. So this is the way to get the real deep dive. Grab yourself the book if you're not one of the lucky 5 to get one today. But good luck to you all. Now we're over to the Q&A section. Now, there were a lot of good questions, and a lot of them were very in-depth. In fact, some of them relevant to the moment you were talking. Perhaps we could have taken some questions by interrupting your presentation. Let's get a question here from Maximilian. Which sniffer software should be loaded on the sniffer USB stick?
Well, on one of the last slides, I've put up the link to the documentation from Nordic Semiconductor. That's just some sniffer firmware that created by Nordic Semiconductor that you can put on their Bluetooth low energy development boards. They have different boards. So this is the dongle, the NRF52840 dongle. They have also the NRF52832 dongle. They have also the development kits. These are the bigger kits. So you have to put the right firmware for this specific device on the right device, of course. But it's all documented in the documentation link I put on one of the last slides. And this documentation, this firmware also comes with the corresponding capture plugin for Wireshark. So you have to install not only the firmware on this device, but also the capture plugin on your computer, so the Wireshark is able to communicate with the sniffer dongle.
Great. And a question from Samesh is, what is the advantage of a dongle over Wireshark?
Well, you need both. The dongle is really intercepting the Bluetooth traffic. It's sending the intercepted traffic to your computer, and you need Wireshark to investigate and to scroll to all these packets and to really do a deep dive into the package, the bytes of the packet. So it's really a combination.
Good point. That takes us to Daniel's question. Is the Bluetooth sniffer visible to the devices it is intended to detect, or is it hiding secretly?
No, it's really a passive form of just sniffing the Bluetooth traffic, the radio signals from the air. So it's not really doing anything. So no, the Bluetooth sniffer is just picking up the packets in the air, just doing it passively. It's not connecting to devices or sending out requests. It's just looking at the traffic in the air. So it's not visible to devices you are trying to detect.
Great. Another good question. Isn't there any encryption over BLE peer-to-peer communication sent over the air?
Yes, I glossed over this detail because there are various types of security. There are different levels of security in Bluetooth defined. You can have no encryption, no authentication. You have encryption but no authentication. You have encryption and authentication. There are different levels, the different types of how to bond with another device, how to pair with a device, how to set up this encryption. But if you're looking at what's on the market, almost all of the devices you will encounter don't use any security. So I could just connect, even my neighbor should be able to connect to this clock and set a time to another time. So it's not really secure. Anyone in my neighborhood could synchronize this time and set it to a wrong time. So that's reality. Most of the Bluetooth devices on the market aren't using any of the security measures that are in the Bluetooth protocol. But if you have such a device that is using encryption, the Wireshark plugin is able to intercept the traffic if you enter the key details, the details of the security key in Wireshark. So it's really an advanced feature, but it's also documented in Nordic Semiconductor's documentation of the sniffer firmware and the corresponding plugin. So if you know your device is using this encrypted or authenticated security level, it's often you can still intercept it, but then you have to know the encryption key, and that's also not always easy to get by.
Okay, the next question is, can't we use the RF system for sniffing instead of a dongle?
I don't know exactly what this person is trying to say with system RF. But yeah, the dongle is just picking up the Bluetooth radio signals and converting them to the known Bluetooth format. So it's quite easy to use. I don't know if it's any advantage to use any other. There are, of course, many. This is a cheap dongle, a cheap way to sniff traffic. If you really want to find out all traffic on all Bluetooth channels, I didn't talk about Bluetooth channels, but there are different channels used by Bluetooth. If you really want to not miss any packet, then you're not going to be able to do it with this cheap sniffer. Then you have to use some professional Bluetooth sniffer hardware that costs thousands of euros. But for just trying to reverse engineer these types of devices, this dongle is all you need.
Great. I mean, I thought perhaps you could use a software-defined radio or try to use the chipset in your laptop. But as you say, this is a really cheap dongle, so it's it's an easy entry into Bluetooth sniffing. Another question here from Jürgen is, can this re-engineering strategy also be applied to non-BLE Bluetooth devices?
I think you're talking about Bluetooth Classic devices. Well, I'm not that experienced with Bluetooth Classic. Most of the devices I've been using recently are just Bluetooth Low Energy devices. I can imagine you could do the same. The strategy would be the same, but you would have to use different tools like the BLE sniffer firmware. Then you have to use a Bluetooth Classic sniffer device. But I'm not experienced with Bluetooth Classic. But the same strategy should be useful with some other tools.
Question from Jose. Does the NRF BLE sniffer bring more information than the HCI snoop?
More information. The information you need for this type of reverse engineering, it shouldn't be a difference. I'm quite sure the NRF BLE sniffer gives some more low-level information, but you really don't need its low-level information. You need just the higher levels parts of the Bluetooth stack, that really what is being sent to what characteristic, what you're reading from what characteristic. This is really on the highest level of the Bluetooth low energy protocol stack, and then it really doesn't make that much of a difference if you're using the sniffer dongle or the HCI snoop log.
Okay, now I think you've got some people paranoid. Sandeep has asked, how safe are my devices? Where can I learn to secure them?
I don't think you're going to be able to do much if you have a device like this one that doesn't secure its connections. Then yeah, you're just having to live with it that your neighbor can set the time in your clock. If the vendor doesn't secure its devices, there's not much you can do, except if you want to re-implement the firmware yourself, but that's a whole other level of reverse engineering.
Then in that case, we have a good question from Guido about the encrypted communication, not one of those insecure devices, but for an encrypted communication via BLE, this task of reverse engineering is almost impossible?
Yeah, if you have a device that is really pretty well developed and it implements the most secure ways to connect, then yeah, it's almost impossible to reverse engineer disconnections in the air, but you can still do the part on the phone. Then you just have to enable the HCI snoop log, because what the HCI snoop log is doing is it's just intercepting the traffic on the phone. So you should be able to see all the packets there.
Thanks, Koen. And we've got your clock here. So I'm looking at your clock, and it looks like we're about to run out of time. So we had some great questions, and we just don't have time for more. But you can always join us on our YouTube channel when we do publish this. If you have any questions, we will check them out there and respond to you then. Now, if you like this webinar, you would be sure to like next week's one. I want to give you a sneak peek at what's coming up next week. Join us for another deep dive, this time into the transformative world of automation. We'll explore how the concept automation is simple is reshaping industries with a special focus on WheelMe's AMRs, autonomous mobile robots. You'll get insights from Saad Imtiaz, a senior engineer at Elektor, who's in the room with me right now, actually, as well as industry leaders Kai Krias-Nemkok and Kasper Roodsrud from WheelMe. So we'll cover everything from the basics of automation to strategies for seamless transition and security considerations. Whether you're an industry professional or just curious about the future of automation, you won't want to miss that. That's next week, this time, 4 p.m. European time, 14 hours UTC. And you can find out all about our webinars at our website, elektormagazine.com. Just navigate to webinars and you'll see what else is coming up. Scan the QR code here and you'll get there as well. Well, thank you for that hour. We could have done another hour, Koen, such an in-depth topic and still so many questions. And thank you very much for joining us. Koen is having connection issues, so I'll turn my camera and Koen will say goodbye there. Looks like his Wi-Fi has dropped out. And thank you, attendees, for joining us. It was a fascinating webinar for me as well. And I'll be sure to watch this again on YouTube because I want to do some more BLE experimentation. Thanks a lot for joining us, and goodbye.